All right, similar triangles. What I'm going to do here is get straight to the point. If you have two triangles that have the same angle measurements, that all three angle measurements are the same, then those two triangles are similar. They will be proportional to each other. Now that rule does not apply to other figures. Okay, if you had two quadrilaterals and the four angle measurements of both of them were all the same, that does not guarantee that those quadrilaterals are similar, because you do have this potential to rearrange the angle measurements from one figure to the next, and then it just does not match up. Okay, but in a triangle, because you are limited to the three angles, it does end up that the triangles would be similar, which would mean that their side lengths are proportional. So we're going to start with another observation, though, that makes things even easier to sort of talk about, because I mentioned it as saying that they have to have the same three angles that go with it. Well, suppose that two triangles of different sizes have two congruent angles, such as let's go with 50 degrees and 60 degrees. Okay, suppose we have two triangles that both have those angle measurements there. What must be true about the third angle? Well, because we already know that the angles of a triangle must add up to 180, the third angle would have to be the rest of that amount. So if these two are going to add up to 110, okay, and they add up to 110, then the third one would have to be 70 degrees. But in your other triangle as well, you've got the exact same situation. You've got a 50-degree angle, you got a 60, you got 110, so that third angle would have to be 70 degrees. All right, so what must be true about the third angles? What would be true about the unknown angles of those two triangles? They'd have to be the same. They would be the same. Or you said that they're congruent, right? In this case, that would be 70 degrees because you've already got 110 accounted for. All right, so what I want to do here is verify that if I've got two triangles with two congruent angles, that those triangles would end up being similar. Not congruent, but that they would end up being similar to each other. Okay, so we're going to go ahead and work with the angles that I had before, which were the 50 and the 60. Now, of course, if both of these triangles have a 50-degree angle and a 60-degree angle, the third angle would be the same, which is that 70 degrees. So what I've constructed so far is the very beginning of two triangles. Okay, now things that I did in particular, though. The first is I actually chose base lengths. I chose that to be 6 centimeters and chose that to be 9 centimeters. My first idea was to make the second one twice as long as the first, but I thought that that would be a little too cliche, do a 1-to-2 ratio. So I thought of doing something different, which would be a 2-to-3 ratio. Okay, so I have that set up. In addition to that, what else I have done is I've started to make the angle measurements, the 50 degrees, the 60 degrees on each of those, but I haven't actually extended them all the way out. So I'm going to go ahead and do that. Okay, so I've got a direction, right? I got a direction of 50. Okay, I'm going to go that way. All right, here's the 60 degrees. All right, and that closes off the triangle, which of course will give us 70 degrees over there. All right, for the other one, there's the 50, 60, all right, it's gonna cut it close. It's gonna cut things super close. All right, so we get that, and that would be 70 degrees up there. Now remember, what we're trying to do here is prove that they're similar, that these would be similar to each other, not congruent. Now they've already got the congruent angles, that part is set. If we can demonstrate that the sides are proportional, that would conclude the idea that they're similar. So let's start with what I already had. This had a measurement of 6. That had a measurement of 9. So if I set that up as a ratio, I've got a 6-to-9 ratio. All right, the other ones, like the other corresponding sides, probably are not gonna look as nice as this because the measurements will be what they are. All right, so I'm gonna go ahead and evaluate this in the calculator just so that I can see it as a decimal. 6 divided by 9, of course, this is 2/3, it's the same thing as 2/3. That evaluates as 0.6 repeating. Okay, so let's keep that in mind. All right, so what I need to do next is take measurements of a couple corresponding sides. For example, let's take the side which is across from the 60, okay? Maybe I should measure on the outside. I should do it that way. Okay, that appears, and this is going to be a little bit tough, okay, so we're going to have to be flexible in what we get. All right, it appears as though it's about 5.6. We go with 5.6. All right, and then the corresponding side, see if we can get that right. That appears to be about 8.3. That'd be about 8.3. All right, and while we're at it, let's go ahead and measure these. That'd be about 4.9. This, about 7.3. All right, now a lot of this is also depending on how well I actually measure those angles with a protractor. Okay, but remember that this evaluates as 0.6 repeating, 0.6 repeating. So we're looking for something close to that. Okay, I'm gonna take these two numbers, 5.6, divide that by 8.3. Okay, we don't get 6 repeating, but we get very, very close to it. We get 0.67, which is really close. And that repeating 6 would actually round off as 0.67. So this is pretty darn close. Okay, we'll go ahead and take these two. We got 4.9 divided by 7.3, which also comes back as about 0.67. So remember how this all starts? We have two angles that would be congruent in the triangles. The third is automatically going to be congruent, so don't really worry about that one. But if we do that, all of the corresponding sides will end up being proportional to each other. Okay, let's go ahead and state our findings as the angle-angle similarity shortcut. All right, notice that it does not say angle-angle-angle similarity shortcut. That's because if two angles are already congruent, the third one has to be congruent as well. Okay, so it says, if two angles of one triangle are congruent to two angles of another triangle, then the two triangles are similar. They would be similar to each other. Not congruent, but they would be similar. So here's a picture that we could show. K is congruent to Y, J is congruent to X. Obviously, overall, they're not congruent because this is smaller than the one that we have here, but the angles are the same here, which means that L and Z would be the same, and therefore you could write this statement that triangle JKL is similar to triangle XYZ. For example 1, we've got a really short problem. We're just simply asked, are these similar to each other? Would these two triangles be similar? Well, to decide that, we just have to show that two angles are congruent. Two pairs of angles would be congruent, that is. All right, so both of them have the right angle. So that'd be one pair of angles. All right, now we've got a 26. We also have a 64. Obviously, those are not the same measure, okay? So that couldn't be our second pair. However, remember that triangles add up to 180 degrees. So we could figure out what this angle is by subtracting these values from 180. Or, because you've already got a right triangle, you could just look for the complement to that angle. So if I took 90 and subtracted 64, surprise, it's 26 degrees. It's 26. So these do match, which also would mean that E matches H, that would be 64. So these are similar. All right, let's go ahead and write a similarity statement for this. We could say that triangle, let's do CDE. Okay, triangle CDE is similar to triangle. Then we just match everything up. C is going to match to K. D matches G, which leaves us with H there. So we could write that as a similarity statement. For example 2, we're going to write one of these shortest possible proofs. We're going to prove that triangle AEB, which is this top triangle here, well, I guess it goes in this order, AEB. We're going to prove that that triangle is similar to ADC. So we can prove that the little one is similar to the larger one that it sits inside of, which that is important that you realize one is sitting inside the other one. All right, so to prove that they're similar, all we really need to do is prove that two angles are congruent. You don't have to prove that all three of them are, because that third angle would automatically be congruent, and that takes us back to our, what we call angle-angle similarity shortcut. You don't need to show all three of them. So, step 1, let's take care of the given. All right, angle ABE is going to be congruent to ACD. All right, and that is given. They told us that. By the way, what that would mean is that this line and that line are parallel. It doesn't really apply to this proof, but that would be true if if these were congruent, we would have corresponding angles, which would make the bases parallel. All right, we don't need it for the proof though, I just wanted to say it. All right, step 2, so we got a pair of angles there. Step 2, we need to identify another pair. Okay, so what other angle does the little triangle and the big one have that would be the same size? Well, that angle would be the angle that's in both of them, which is right up here at angle A. Okay, in the little one, you've got angle A up at the top. You also have that at the top of the big one. So we don't know the measure of it, but we do know that angle A is congruent to angle A. That would be the reflexive property. All right, so that's two pairs of angles. You could almost imagine these separated from each other, that you have the little triangle, top angle, bottom right are the same with the top angle and bottom right of the larger one that we got there. All right, so if we do have two pairs of angles that are congruent, 3, we can state this. All right, we can go ahead and state that the triangles are similar because of the angle-angle similarity shortcut, which I'll just abbreviate as AA. And that's it. That's the whole proof. Only 3 steps. All right, and last what we have is one of the most traditional similar triangles problems. What we do is we use proportionality to figure out the measurement of something that we otherwise could not measure. In this case, the item that we couldn't measure would be the height of this lamppost. All right, so the problem says here, a person 5 feet 3 inches tall casts a 6-foot shadow. All right, so here's our person. It says 5.25 because 3 inches is 1/4 of a foot. Okay, so it's not 5.3, but it would look like 5.25 because 3 out of 12 is 0.25. All right, so there's his height, just in feet, 5.25 feet. His shadow is 6 feet long there. Okay, so those are measurements that we could figure out. All right, so then over here we got a lamppost with a height that we might not be able to measure, but the shadow, being that it's on the ground, you could take that measurement and say that it's 18 feet. All right, so at the same time of day, the sun is creating these shadows. So at that time of day, the sun has a certain angle of elevation, okay? And that angle of elevation would be the measurement here. So if you were to look up from the ground at the sun, it would be that angle. Okay, and if this is at the same time of day, the angle of elevation here would be identical to the angle of elevation that we have right there. So we need to first make the statement that these two triangles are actually similar to each other. We're able to do that because they both have that angle, that same angle of elevation, and both of these things, this person and this lamppost, are at a perpendicular when we measure their height. All right, so by AA similarity shortcut, these two triangles are going to be similar and therefore proportional. Okay, so as a proportion, I could take these values, okay, set them up as a ratio or a fraction, set that equal to what we'd have over here with the corresponding parts. That would be x over 18, and then simply do cross products. Okay, take that product, see what that would look like. We got 5.25 times 18. Okay, we get that. Divided by 6, get 15.75. All right, and then if you were inclined to do so here, because everything's in terms of feet, we could call this 15. We could call it 15 feet, and that would be 9 inches. That's what that would be.
Later, blah.
They've already got the same angle measurements. Interrupted by a bell.